wel twee derde gemiddelde zit altijd onder het echte gemiddelde. En iedereen moet hetzelfde kiezen, dus de target score zit altijd onder de score die iedereen zoekt. Dan moet je dus alleen laten zien dat als iedereen hetzelfde.
All right. I uploaded the slides on Canvas. Can somebody check to see whether they're online, right? Okay. Okay. So we discussed a lot before about why generative models, why not generative models, what you can do with them, and so forth. And we also saw that distributions are basically the language on how to language in quotes on how to think about deep generative models. So why not even ask why probability distributions in the first place? Well, our goal, we don't really care that we've got probability density. At the end, what we really care about is having a function that returns good images or good data points or whatever. If you want to do statistical inference, of course it makes sense to use probabilities because that's how you define how you do the statistics. But if you care about generation, so generative models, you don't really need that. That's not. However, you do want to learn a function that is like good enough to return good generations, good new data sample, which means that you have to find the best possible parameters, and maybe these are not even that great, but well, anyways, you have to find the best possible parameters of your function that generates plausible new inputs. So of course, there are two obvious questions. One is, how do you find these optimal parameters in the first place? And second is, okay, let's say you got them, how do you make sure that they are indeed plausible, like these generations, as well as diverse? It's trivial to make a function that returns a new image. I can write a script, I download a picture from Google, and they keep sharing the same image. But of course, that's not the point, right? Like, I want diversity, and I want a model that actually learns to do it itself. And well, probability distributions give good answers to both questions at the same time. So you can use the probabilities to optimize for maximum likelihood estimation or other similar metrics to find the best possible parameters data for your model, right? I just want to maximize my likelihoods, that's it. So that's how I say I find the best possible data. And how to generate plausible and diverse new data points. Because I've got a probability distribution in the first place, then it means I can sample from it, or at least I can define algorithms to sample from it. If my distribution is Gaussian, it's obvious. If it's non-Gaussian, something like non-canonical, then you have to find ways that you sample in a fair way. Basically, sampling is one of the biggest tasks, objectives in machine learning in general. How do you sample from non-canonical distributions? Either way, probability distributions offer these two very nice and convincing answers to two main problems, and that's why we go with probability distributions in the first place. Otherwise, they can be quite limiting, right? Like you have to, well, we'll see about it. So, distributions are, well, I wouldn't say strange beasts, but they're not always, they come with constraints, modeling constraints. If I have low dimensional data, for instance, SAT scores, we can just plot them and like see what it looks like, right? Like, I guess you see that, what does this look like? A Gaussian, right? So, that's just statistics. You plot the data, You see what it looks like? So it looks like a Gaussian. Let's compute the mean and the variance. You compute the mean and the variance of this population, NP mean, NP STDev, and that's it. You've got your Gaussian. Like you've got the two parameters. So in this case, for a Gaussian, my parameters theta. So the parameters theta that define the model, the parameters theta that if I have them, I can know everything about my model in terms of sampling, like inference, whatnot, probabilities, is this mean and variance. And for a Gaussian, it's very easy to compute mean and variance, right? Like you just take the mean over all the SAT scores, or the variance over all the, and the variance over all the SAT scores, and that's it. You will have a perfect Gaussian that hopefully is going to match very well what you see in front of you. And once you've got that, you can sample, right? Like basically you can sample new SAT scores. It's going to be samples from the Gaussian. It's not going to be real SAT scores like the people have taken, but they will fit the distribution perfectly. However, our data is not always that simple, that low dimensional, that intuitive. This, you can say it's just one dimension, right? How many dimensions does this data have? Well, let's say it's 1,000 by 1,000 pixels, so 1 million pixels overall, right? So basically 1 point, like once SAT score is one dimension, this has 1 point, 1 million dimensions. Now imagine if I plotted in this one-dimensional space with a histogram, do you think it would make a Gaussian shape? It will have a Gaussian shape? Yes?
Well, if you have RGB pixels, it will be 3 million, right?
Yes. Sure. When you've got RGB pixels, of course, it can be even larger, of course. So when we've got images or harder, more complex data, we cannot simply rely on canonical distributions to define a generative model over them. We cannot say, you can say that. You can compute the mean per pixel or the variance per pixel, or you can even compute the mean over all pixels and make it like a simple bell shape. But obviously, you wouldn't expect that from this Gaussian you can actually generate new images, right? Like, that would be absurd. And the reason is that this data point, even by the sheer dimensionality of things, cannot fit the Gaussian easily, right? Like it's like so high dimensional. What are the chances? Like most of the space will be empty. You cannot expect it to be Gaussian per se. So you need to have different ways, alternative ways, to learn functions that are probability distributions, which are also non-canonical. They're not just Gaussian. They're not just like, I don't know, Bernoulli or categorical distributions for discrete data and so forth. You would like to have indirect ways, perhaps, of learning these distributions. Well, indirect in quotes compared to Gaussian, to simple Gaussian. So you need more flexibility. Is this clear here? So beyond canonical distributions, what is a distribution? What is a probability density function? Well, there are three main, axioms, three main laws for why a function is a probability distribution. Well, and I guess we did more like, you've done it before, I'm sure, more or less. But basically, the three rules that are called Kolmogorov axioms, for what it's worth, is that our probabilities have to be positive, right? I cannot say it's minus 20% that it will rain tomorrow. This doesn't make sense. The probability of all possible events should sum up to 1. So, well, it's either going to rain tomorrow or it's not going to rain tomorrow. Both events are 100% like together. They're 100% probable, right? Like one of the two will happen for sure. And the third one, so that's the second. So omega is the space of all possible outputs. X is the space of all possible events, samples from event space. And then the third axiom, the third rule is that basically if I take disjoint sets of events, their total likelihood is the sum of the individual disjoint sets, like the likelihoods of the individual disjoint sets. So it's a sigma, right? So here you decompose it. So if tomorrow is, well, what is the weather tomorrow? Like it's either going to rain or it's not going to rain. So it's the sum of the probability of raining plus the sum of the probability not raining, and together, of course, have to sum up to 1. If we have functions, if we can define functions that satisfy one way or the other these axioms, then that's it, we're game. Of course, it's not important just to define such functions, you have to learn them as well, right? Like we're doing deep learning here, so you have to use ideally a neural network which satisfies these 3 axioms like by its construction and by its learning. How can we satisfy the first one? Basically, P, let's say P here is my neural network, right? Like it's the output of my neural network. So my neural network is a function that returns probabilities as outputs. X is my image. Is this a cat versus not a cat? And I would like to make sure that my probability is positive. What do I do? Yes?
You use a ReLU at the end?
Yes. So more generally, you can use a function that has only positive outputs, right? Like a ReLU, a sigmoid, an exponential, x squared, whatever. Of course, such a function has to also, that's just one of the 3 axioms, right? But if we were to care only about the first one, any function that returns positive values is permissible. And about the second and the third, do you have an idea? How do we make sure that basically we have the total probability space is 1? Yes?
You can normalize the output by, for example, using a softmax.
Exactly. So, for the first, let's say, axiom, it's easy. You just need to find positive functions, and that's like your set. It can be an x squared, it can be an exponential, and whatnot. For the second one way, it's not the only way, but one way is that you've got a function that returns any value, positive, for probability. Then you go over all possible inputs. You compute the output of the function, so f of x, for all possible j's, or an integral if your x is continuous, and then you divide by that. Then if you were to take the sum of this p of x or the integral of p of x, that would be 1, right? Because that would be sum of f of x over z, which is sum of f of x. And then that's by definition 1. So the second one would be satisfied, and the third one would be also satisfied because of the sum, because of the way that we decompose the function, right? Like the total probability is the sum of the individual probabilities. Is this clear? What could be problematic here? This is easy, right? Like that's just a positive function. I put whatever number, like it always positive. What can be problematic here? Yes?
Well, like we said, there's a lot of images that you can generate, and I think going over all the images is just not reasonable.
Why?
Because there's almost infinitely many, and if you just want to loop over every image and compute the function, that's going to take a very long time.
Right. So computational efficiency. That's a very important argument, because here we don't do math, right? We don't. I mean, we use mathematics. We can even say that people invent new math, or we use very fancy math. But in the end, we want to model data. And when it comes to modeling data, computational efficiency is almost as important, perhaps even more important. In the question model versus scale, clearly scale has now given a very bold answer, which means that things have to be computationally efficient, otherwise you cannot really scale up, right? So, indeed, how would it look if I have now a picture of 1 million dimensions? So my x is 1 million dimensional vector, right? I have to take here my image here, xi is this x1, that's the first pixel, x2, x 10 to the power 10 to the power 6. So I've got 10,000 dimensions. Sorry, 1 million dimensions, right? I have to compute my function f, my likelihood, if I were to take this approach of normalization. I have to take the f of x. So this is the f here. For all possible inputs or all possible images. Even in the simplest case that I take binary values, so x. Okay, let me make here the dimensionality so it's not confusing. Even if I say that my pixel values are only 0 or 1, so black and white image, you have to go for all possible permutations, like this is 0, 0, 0, 0. Then the next one 0, 0, 0, 1. And then forever. Like that's just impossible, right? So computational efficiency is a huge aspect to take into account here. However, you might have the problem of simply like not possible to compute things analytically. So computing the integral, and I use here the integral because that's the more general, let's say, form here for the normalization constant, can be very complex or even intractable when you have many dimensions. So even the number of dimensions alone is a huge problem. But you know, what if your function f, together with probabilities and so forth, whatever, you've got a complex neural network, you've got like, you choose weird nonlinear functions. You cannot simply analytically compute the integral, right? Like it's just not, like there are no solutions for that. So how do you actually compute it in the first place? So you either have to find convenient ways to compute the normalization constant, either approximately or precisely by making specific modeling assumptions, such that computing the integral is easy. If, for instance, I would say that my function is an exponential, whatever, like then finding the integral of an exponential function is easy. If I were to say that my function has a much weirder parametric form, then things become more complicated. I cannot have one equation that gives me direct access to what is the normalization constant. Or we have to pick functions that satisfy all these three axioms by construction. So I don't do normalization constant per se. I pick a model family for which the normalization constant is already in a convenient form. Or you can even ignore it because you don't really care about it anymore. It's implicitly there, but you don't have to explicitly take it into account. For instance, autoregressive models or flows or latent variable models or other. There, you don't really, I mean, it's still, you cannot avoid it, it's there, but it's implicitly taken care of. So generally, I would say that the tale of deep generative models is about the story of making intractable things tractable one way or the other, and then being able to say how good your solutions, your tractable approximations or your tractable solutions are compared to the actual reality of your data. Like, that's it. Generative models are complex to solve because of this intractabilities everywhere, be it for the normalization constant or other similar familial quantities. They can also be intractable because of computational issues. Like, I could do it, but I just can't loop over my images, certainly not for every mini batch in my gradient descent step. Okay, step. Intractability can be in the likelihood estimation, like in the forward propagation. It can be in the optimization, in the sampling, when you want to sample, right? Like, can I sample in an efficient way? Can I sample in a tractable way? On the inference, if we have inference steps, if we have latent variables. And usually we solve intractability by strong assumptions one way or the other. For instance, with VAEs, we make a variational approximation that we'll discuss next time. And hopefully, like, this variational approximation is by nature, by definition, tractable. We make this assumption. We assume that we have a specific distribution that we can easily compute. And we hope that this approximation is going to be close to the reality. Like in my previous example, we make the assumption of the ellipsoid. Basically, ellipse is a Gaussian, and we hope that it's going to be good enough. And often it does. Look good enough. Autoregressive models assume causal convolutions, normalizing flows, assuming invertibility in layers so that you can easily, well, so that you can compute the likelihoods, the probabilities. And, you know, what model is best or what works is the question. Like, all of them are generative models. Some of them are better, some others are not. Why is that the case? Do they learn better probability descent functions? Yes. Why? It can be the approximations, it can be the sample efficiency, it can be a lot of things. So, in other words, to rephrase, deep generative models is a battle between tractability and flexibility. These are the two opposing forces. If that's our reality, like that's a joke that I learned from Jakob Tomczak, an expert in deep generative models. So these are like what our cows look. Quite often, we make an assumption. We assume that cows are spherical, and we try to model the world of cows like spheres. Clearly, that's not a great representation for what a cow looks like, right? But it's tractable. Spheres, we know. We can make them larger. We know like their circumference, their radius, their like volume. We know how they expand in more dimensions. They're nice. They're comfortable. So tractable models are usually, at least, analytically computable. So we can do computation very well, very easily, very comfortably. It's easy to evaluate and fit. However, again, usually they're not flexible enough, or we cannot be guaranteed that it's going to be flexible enough to fit the true data structure. We assume the latent space is Gaussian. We cannot know that for sure. If it is, if our data is like has a Gaussian latent structure, then it's a perfect fit. If it doesn't, then we have to be like, you know, we have to do the best possible, and we hope that the best possible is not too far away from reality. These are about tractable models. Flexible models can fit arbitrary structures in the data. However, they're more expensive often to fit, to sample from, to evaluate. So for instance, autoregressive models are more expressive. They can fit every distribution, but computing them is hard. Any questions here? So a minimum viable definition, step by step. This is our deep generative model. Typically, P is the family of generative models that we pick. Is it like a latent variable model? Is it a normalizing flow? Is it a diffusion model, a score-based model? What? Like, you have to pick something. That's You say that's my probability, like my deep generative model family. In the second step, we have to decide how we will implement the function h that is our input to our deep generative model. If x, let's say, is our image and h is a neural network in the context of deep networks, which deep network makes sense for our data? We have to decide that. Is it going to be a ResNet? Is it going to be an LSTM? Is it going to be an autoencoder? You have to make an explicit decision there. Neural networks, like there are better and worse versions, right? Like also for discriminative learning, not all deep networks are equivalent. They're all universal approximators, but they're not all equally good in practice. We have to find the good one in the end. Yeah. Also, we not parse all the image, so we are going to, that's another point to consider. When we've got an image, do we use the whole image as input? Do we consider each pixel sequentially, one after the other? That's what you do for autoregressive models. Will my function return binary outputs? Is it going to be Bernoulli distribution? Like if it's black and white, that makes more sense. Is it a discrete output? For instance, I've got pixels from 1 to 256 for 256 classes, then I have categorical distribution. Is it like a continuous output? Then you have to have perhaps another one, like Gaussian distribution or some other distribution. So you have to make an explicit assumption for the output. Do I want to make my layers invertible? What does this mean? Like I can easily go from the input to the output or from the output to the input, like explicitly and analytically. There's one-to-one match. This is what you need, for instance, when you've got normalizing flows. Clearly, this is a stronger constraint. Functions are not. There are many more non-invertible functions than invertible ones. How do you design a neural network such that it is invertible, such that you can go backwards? That's another type of neural network design that we have to take into account. Is this clear so far? Questions? Yes?
Doesn't the way we choose H affect the family?
Yeah, of course. Like these are not in isolation, right? Like if for instance, if you have a Bernoulli distribution, then your VAE loss function will change. Perhaps you will not have mean squared error in the first time of your elbow. You'll have like gross entropy. Of course, the effects. Not, of course, all the choices here will affect all the choices there. But there is a link you cannot ignore. Step 3: how to learn the optimal parameters. Okay, like I defined, like you can define whatever you want. Like the point is that you actually want to learn something in it. So, what is our loss function? Usually that depends on the previous two choices, right? Like what probability distribution family probability distribution function I have picked, Bernoulli, categorical. What kind of family of general models have I picked? Is it like a VAE, latent variable model there? That is. Is it an autoregressive model? If it's not autoregressive, then I can do maximum likelihood estimation because I can compute the precise likelihood for my image. Like whatever my image is, how many million dimensions I have, assuming that I can do it fast enough, I can compute the actual likelihood for that input, given my model, of course. I don't make any approximation. So this means that I can compute the maximum likelihood estimation. I can find the model parameters that give me the best possible likelihoods for all my inputs that I've seen so far. If I have a latent variable model, however, I cannot do that. It's intractable to compute the precise likelihood. So what else can I do? Well, an often desired objective is to minimize the difference between my learned distribution and the true distribution, which, however, is a chicken and egg problem because I don't have the true distribution in the first place. So you have to find now a way to measure the difference. And we're going to discuss this in a subsequent lecture. So find ways around gives also rise to different types of, different families of generative models. Questions? How to optimize? Okay, let's say now I know what I want to optimize. How to optimize? We must pick an optimization algorithm. It's better to start with simple solutions. So that's something that I see a lot of, especially students, do. They go for the most complex solution right away. I can tell you with very high confidence that indeed Adam with the standard hyperparameters will work best. However, it is good practice from, let's say, modeling perspective, from a coding perspective, to always start from the minimum model, from the simplest possible choices, because like that you can always increase complexity in a controllable manner. If you start from the most complicated model with all the bells and the whistles, you don't really know what is truly needed, what you can remove and become more efficient, or what causes the problem actually also. Of course, that's not the black and white. Things are complex. What is the simplest possible model? You have to think about it. But in general, make conscious decisions. Don't just like download a model or code and then run it like that. I mean, okay, you can also do it if you want to just explore a bit. But if you're in the development process and the design process, make conscious decisions. Then we start training. We minimize loss. We monitor our whatever metrics on a held out validation set. Keep training. So with deep generative models, you have to train a lot. It doesn't really matter. Then you can also optimize your hyperparameters. Usually with grid search, Bayesian optimization, Hydra and whatnot. Another problem that I see with students is that they try to, hyperparameter optimization is really like a luxury thing, right? Like back when I was doing my PhD, we didn't really, okay, you more or less knew what the good hyperparameters were. Usually that was, the models were not that sensitive in general. I know that now neural networks are quite sensitive, so you have to be a bit careful. But it's unlikely that bad hyperparameters will be the reason for bad performance. Usually you can do better and better with better hyperparameters, but you have a good grip of what will work more or less. And that's a good starting point. Don't waste time and resources on hyperparameter optimization that might change when you actually have a better model, like in 3 days from where you're at the moment. Now training is done. What can you do? You can compute likelihoods for new inputs for one, right? You can compute probabilities or whatever other statistical inferences you have on your variables. This is like the forward step, in your training. You can also sample. You can sample new pictures, new images. If you have an algorithm that can sample. Again, think about it. We don't have Gaussian distributions or canonical distributions. If you have canonical distributions, sampling from them is straightforward, like np dot rand n. You sample from a Gaussian. When you've got a very high dimensional non-canonical distribution, how to sample? You can do all sorts of hacks and tricks. Like I start from my training image and then I do a grid search, I follow, I add here, I add there a bit, and then, but that's not really sampling, because what sampling means in the end is that if you were to sample for long enough, you would be able to obtain empirically the true distribution of your data. So sampling is not non-trivial, a fair way of sampling. Also, is our sampling efficient? For instance, autoregressive models are sequential, which means that to generate my next pixel, I have to first wait for my previous other pixels, and so forth. So to generate the 10,000th pixel, I have to go over 9,999 pixels before that. Have explicitly one forward computation for each of them. If you have an autoencoder, that's just one call, right? Like you don't do it 10,000 times or a million times. And of course, per model, we'll have more steps. How to do inference with latent variables, gradient computations, e.g., for instance, when you have discrete variables, you cannot easily compute gradients. They're discrete. We've got discontinuity. You might want variance reduction because you have random variables. If you have random variables, this means that the output of your function might be very large. Like every time you throw a die, it might be like a very different, like widely different outcome. The bias might be very low, so you might be on average getting consistent results, but the range is so large that it's actually a problem for the model. How does the model know, the true underlying mechanism if the outputs, although correct, are very wild? So overall, challenges for generative models. How to make sure our model computations are tractable. How to find the right type of model for our data. How to optimize for the best parameters. Especially when things are technically intractable. How to sample, how to do inference, how to do learn representations if we want to learn representation. Not all generative models learn representations. Like autoregressive models don't learn, for instance, representations. Or diffusion models don't really learn representations. You cannot take one of the layers and use it comfortably, conveniently for a classification afterward. So the things that you have to keep in mind is that when you've got a generative model, you have to have well-defined forward and backward computation steps. You have to have algorithms for how to do inference when you've got latent variables, like with VAEs. You've got a variable that you actually literally do not know what values it takes. And to add to that, these values have to follow a particular distribution. How do you compute these new values, these hidden values for new inputs? You have to make sure that all these algorithms are not too complex, that they are efficient enough. You have to define the learning objective and the optimization, like what you're actually aiming for. You have to implement the neural network, and you have to determine how to use them for downstream tasks if you want a downstream task afterward. And very quickly, families of generative models, based on that, on all these complications and all these challenges and all these steps that you have to take into account, there are different families of generative models that make some things easier, some things harder. You have to choose what is best for you. If you're maximizing your likelihood estimate, then you can do explicit density or implicit density. And if you're optimizing for explicit density, you can have approximation of it or the true one, tractable density, like change of variable models, like normalizing flows, or autoregressive models, like pixel RNN. For approximate density, you might have variational models, or Markov chain models. Like these are also approximate the normalization constant, like energy-based models. If you don't care about having the actual density, so you don't really care about doing statistical inference, you just want to generate new pictures, then you are falling in the category of implicit density. And then you can have, for instance, GANs. Basically, GANs are the main, like they're a branch on their own, basically. Yeah. So here there is like this one as well, but yeah, okay. Now, each of them has its own pros and cons. For instance, autorecursive models are stable. So this is from the book from Jakub Tomczak. Highly recommend, very nice book. And by the way, it's also a good moment to say that this time I will also give a lecture notes. So I'm writing basically what I described here in a not too long text, and I'm gonna share it with you like soon after, like today. So autoregressive models are stable. You can compute exactly the likelihood, so you can literally compute the likelihood without any approximations. However, they have slow sampling, and they're lossless in compression because basically you compute the exact likelihood. So if you compute the exact likelihood, you don't make an approximation, you don't lose anything. Of course, the model is as good as it is, but it doesn't lose explicitly information by design. It doesn't learn representations. You just learn the probabilities for your pixels, and that's it. You don't learn representations. You don't learn codes for those pixels. Flow-based models, like normalizing flows, have stable training, exact likelihood. There's something can be fast or slow. It depends on like the data. Lossless compression and representation capabilities, but normalizing flows have an invertibility constraint. So you have to have neural networks that have a very specific structure, such that you can go back and forth, like analytically and tractably. So not all neural networks are possible. Not all like connectivities or nonlinearities are possible. Implicit models like GANs are more unstable. Yeah, like mode collapsing or whatnot. They don't compute likelihoods. However, they have fast sampling. They've got no compression and no representation. Prescribed models like VAEs, data models, are stable. They've got approximate likelihood. They are very fast. Loss compression because they make an approximation step, so you always lose something. And give representations. And energy-based models are stable, unnormalized, the likelihood estimate. They are slow in sampling because you have to rely on the Monte Carlo Markov chain step. Yeah, and compression is not great. However, they have representation capabilities. Questions here? So here is basically name dropping because we haven't really seen any of these families of generative models, but in the next lectures we're going to discuss each one of them. Score-based models and diffusion models, you could say, belong in this category, but we're going to have an explicit lecture just on them because they're really working really well right now. Yeah, so I don't expect you to remember all this. Like the slides I will give anyways, but it's good to have a good, overview of what model is good at what, so that you can expect things and condition your brain for the lecture. Yes?
What kind of model does ChatGPT use?
ChatGPT is not a probabilistic generative model, but I think, or it's like, I think it's not a regressive model basically. So it's really here, like in this slide. So yeah, no, it is a. I think I have to check. It's for sure. It's not like a pure. Like it has like all sorts of like additional losses and like training hacks and whatever. So I mean that doesn't make it any less impressive. If anything, it makes it more impressive. It also shows what are the limitations in general of this perspective of generative models. Like I have to write my math and then it's like work out perfectly. No. Generally, that's something very important to keep in mind in general. I used twice general. Okay. Yeah. So like for whatever you do in your papers, in your work, in your like studies, your models, your approximation, like your math, is only as good as your assumptions, as your approximations. There is no perfect theory usually. You have to make an assumption at some point. If this assumption matches the reality, then usually the model is good enough. If it doesn't, then it's not good enough. So you have to be very aware. That's why you should not just download something and use it. You have to be very aware of what you download and how you use it. Wrapping up. We discussed what are the generative models, right? Why should you care? How to use them, as well as what are the steps that we need to consider when developing one. It's a lot of steps, clearly. But that's also fun, like trying to understand. My opinion, I've tried to understand them in general. Like it's not as hard as they like you might think, or yeah. At the end of the day, you just care about having valid probability computations and making sure that you can do it in a tractable, efficient way. Like that's it. And every time there is an intractability or a computational bottleneck, how do you actually overcome that? we also discussed about like a very brief overview of types of models. So yeah, and this is it. Further reading. I also use this material as inspiration, but among other things, papers and whatnot. Also, Stanford's course by Stefano Ermon, like world expert in the topic, as well as the book by Jakob, which is very nice and comfortable reading. Feel free to you know, like browse through them if you have the time. Stefan Erman is actually also one of the researchers that developed score-based models. And yeah, this is it. Thank you very much. If you have any questions, please let me know.